Okay, so hi everyone. In this video, I am going to discuss about the dining philosopher's problem, which is also one of the classical problems of synchronization. So what is indeed a dining philosopher's problem? So if you want to have a short version of the animation or a fun animation, you can watch this video that I have linked in the PowerPoint. All right, so this is the setup of the dining philosopher's problem. So there are four philosophers that are on the dining table. P0, so represented by P0, P1, P2, P3, and then P4. And um, each of these philosopher only has two states, which is either thinking or eating. And as you can see here, in between each of the philosophers is one chopstick. And in order for each philosopher to eat, they will be needing two chopsticks in order for them to eat. So if P4 is eating, so making use of these two chopsticks, that means that P3 and then P0 will have to wait until P4 is done eating before either of them can start having their own meal. Okay, so how is this relevant to the operating system synchronization problems? So the philosophers represent the processes, and the chopsticks represent the resources or the shared resources in between these processes. Okay, so how can we manage this problem such that all of the philosophers will be able to eat, okay, and not one of them will starve and will be waiting to get hold of a chopstick and will be able to eat for a long time. Okay, so again, there are five philosophers, and in between each of these philosophers is a shared na chopstick. Okay, as I mentioned earlier, each philosopher has two states. One is thinking, and when a philosopher is thinking, there are no interaction with the rest of the four philosophers. And another state is if a philosopher gets hungry and starts eating. And if a philosopher eats, it needs two chopsticks at hand. So basically, if this P4 is eating, it needs these two chopsticks adjacent to it. The chopstick on its left and the chopstick on its right. And another rule is that a philosopher can pick up a chopstick one at a time. So it it's not true that if P4 is hungry, it picks up both of these chopsticks at the same time. So it can only pick up um, this chopstick on its right, or and then the chopstick on its left, or vice versa. Again, the person cannot pick up the two chopsticks at the same time or simultaneously. And another rule is that one cannot pick up a chopstick that is already at the hand of a neighbor. So essentially, if P4 is already eating and got hold of these two chopsticks, and P3 is also hungry and wants to eat, it can no longer pick up this chopstick since P4 is already using it. Okay? And if a certain philosopher is done eating, it goes back into thinking. And if it is done eating, it puts down both of the chopsticks simultaneously. Okay, so how can we solve this tiny philosopher's problem? We can actually do it with semaphores. So what we can do is to represent each chopstick by a semaphore. And we can use the standard operations wait and signal on the semaphore. So assuming that P4 is hungry or philosopher 4 is hungry, it can try to grab a chopstick by executing a wait operation on that semaphore. And that semaphore that we refer to is the chopstick. So basically, each of these chopstick is a semaphore that has a state of either 0 or 1. Okay? So let's say P4 is hungry, it tries to grab these two chopsticks. Okay? So if both of these chopsticks are available, then we change the state of those chopsticks into 0, meaning unavailable. So essentially, when a wait is executed, it implies that the philosopher wants to use that chopstick. And if the philosopher gets hold of it, then no other philosophers will get hold of it. And if P4, let's say, is done eating, or a certain philosopher is done eating, it can release the chopstick or put those chopstick back into the table by executing the signal na operation. Okay? Remember, if we want to execute a signal operation, we are basically releasing a shared na resource. Okay, so this is how you can visualize it. As you can see, we have these 5 philosophers represented by P0, P1, P2, P3, and then P4. And in between them are the chopsticks. Okay, and we represented an array of chopstick na semaphores, all initiated with a value of 1. So 1 means that the chopstick is available, and 0 means that the chopstick is being used by a philosopher. So initially, all of the philosophers are still thinking, right? So they just sat on the dining table and they are not hungry yet. So they are still thinking. So of course, naturally, each of these chopsticks will be available and are set with a value of 1. Okay, so let's say P4 got hungry and took hold of the chopstick 4 and the chopstick 5. So we basically just have to toggle the state of chopstick 4 and the chopstick 5 into 0. So does this sound familiar to you? So we are basically using a binary semaphore, wherein a binary semaphore has only a value of 0 or 1 that indicates their availability. Okay, so now let's have an example. Assuming that P1 is hungry and P1 wants to eat. Okay, so this is the source code here. And of course, if one of our rules is that if a philosopher is hungry, it can only pick up the chopstick on its right and on its left. So first is it can pick up the chopstick on its right. Okay, and if initially the value of the chopstick 1 is equal to 1, which means it is available. So since it is available, P1 can pick it up, and now since this chopstick is already under P1 or in P1's hand, then we set its value into 0, meaning it's already unavailable. But in cases wherein the chopstick 1 is being held by P0, then naturally P1 has to wait. All right. So, and then what happens here if this is not yet available, if chopstick 1 is not yet available, then basically this will keep on looping and it will not be able to, then P1 will not be able to pick up the chopstick of 2. Okay, so now chopstick 1 is now in P1 and it can now try to pick up the chopstick of 2. Okay, and what we do here is we have the operation I plus 1. So we have philosopher 1. So in this case, I is equal to 1. So initially, it picked up chopstick of I, which is equal to 1. And then next is it tries to pick up chopstick of 2. So you can see here that we have it picks up I plus 1 or 1 plus 1. And this evaluates a chopstick of 2. But we have a modulo of 5 here. So 2 modulo 5. So later I will explain why we have a modulo of 5 here. But naturally, this will actually evaluate into 2. So P1 picks up the chopstick of 2. Okay, so since 2 is less than 5, it cannot be divided by 5, so the remainder is 2. Therefore, 2 modulo 5 is equal to 2. Okay, so since P1 has now the chopstick of 1 and chopstick of 2, which is on its left and right, so P1 can now eat. Okay, so assuming that philosopher 2 also got hungry. So P2 tried to pick up the chopstick on its right, which is chopstick of 2. But initially, chopstick of 2 is equal to 0, which means that it is being used by another philosopher. And you know that P1 is already eating and is using that chopstick of 2. That means that P2 must wait for P1 to finish eating so P1 can put down the chopstick of 2 that P2 needs. So since this is semaphore, so we basically just reduce its value, so indicating that it's waiting. Okay, and now P1 is done eating and goes back into thinking and releases both of the chopsticks, the chopstick of 1 and the chopstick of 2. Okay, and now the chopstick P2 can now then pick up this chopstick of 2. So that's why it is 0. And also, the P2 can also pick up the chopstick of 3. So that is, since we have philosopher 2, this is supposed to be philosopher 2. So 2 plus 1, that is 3. Modulo 5, that is still resulting to 3. So it can pick up the chopstick of 3. So you can see here that the chopstick of 2 and the chopstick of 3 are now equal to 0. And P2 is now eating. Okay. And now, why do we need the modulo again? So assuming that we have the philosopher 4. And philosopher 4 is hungry. Okay. So, of course, since P4 is hungry, it needs the chopstick of 4 and the chopstick that is next to it. In this case, P4 is seated next to P0 since this is in a circular manner. So it needs the chopstick of 4 and the chopstick of 0. So if we just have the chopstick of I plus 1, this will result to chopstick of 5, right? But in this case, we don't have any chopstick of 5 since we only have this chopsticks, limited amount of chopsticks, and P4 is next to P0, so it needs to pick up the chopstick of 0. Okay, so the modulo allows us to pick up this chopstick of 0. Okay, so see, if we just have chopstick of I plus 1, that is chopstick of 5, that will result to nothing. But if we have 4 plus 1 modulo 5, that will result to 0. And that allows us to pick up chopstick of 0. Okay? All right. Now, have I solved all the problems? And what could possibly go wrong? And imagine if all the philosophers pick up the chopsticks on the right. So essentially, what happens is they all go hungry. All of these philosophers all go hungry, and they all pick up the chopstick on the right. So P0 picks up chopstick 0, and then P4 picks up chopstick of 4, P3 picks up chopstick of 3, P2 the chopstick 2, and then P1 the chopstick 1. So note that they can only pick up one chopstick at a time. So that is possible. So suddenly, bigla silang nagutom. So okay, pick up ako ng isang chopstick muna. Then suddenly, since they all did it simultaneously, what happens is, ayun. So, isa lang yung chopstick na nakuha nila. And note that you can only eat, or a philosopher can only eat, if they have 2 chopsticks. Okay? So this will result to philosophers waiting on each other to get the resources that they need. And this will result to a loop of waiting among the philosophers. So this will result into a deadlock. So how can we avoid this deadlock? So there will be several solutions to the deadlock problem. So we can allow at most 4 philosophers to be sitting simultaneously at a table, or we can allow a philosopher to pick up her chopstick only if both chopsticks are available. And we can use an asymmetric solution. Thus, an odd philosopher picks up first her left chopstick and then her right chopstick, whereas an even philosopher can pick up her right chopstick and then her left chopstick. And in the next topics, we will discuss more another solution to the dining philosopher's problem, which is using monitors.